Okay, now we're in section 18.6, household circuits. Um, all right, have to advance that. Um, let's talk about household circuits. In a typical installation, the utility company distributes electric power to individual houses with a pair of wires or power lines. Electrical devices in a house are then connected in parallel to these lines, as shown in the figure. The potential difference between the two wires is about 120 volts. Uh, Actually, the currents and voltages are alternating currents and voltages, but for our discussion right now, let's just assume that they are direct currents and voltages. One of the wires is connected to ground, and the other wire, or sometimes called the hot wire, is at a potential of 120 volts. A meter and a circuit breaker or a fuse are connected in series with the wire entering the house as indicated in the figure. In modern homes, circuit breakers are used in places of fuses. When the current in a circuit exceeds some value, typically 15 or 20 amps, the circuit breaker acts as a switch and opens the circuit. The figure shows one design for a circuit breaker. Current passes through the bimetallic strip. Its top bends to the left when it gets too hot because of excessive current. If the strip bends far enough to the left, it settles into a groove in the spring-loaded metal bar. When the bar drops uh, enough to open the circuit, then the bar drops enough to open the circuit at the contact point. The bar also flips a switch that indicates that the circuit breaker is not operational. After the overload is removed, the switch can be flipped back on. Circuit breakers based on this design have the disadvantage that sometimes is required for the heating of the strip for the heating of the strip. So the circuit may not be opened rapidly enough uh, when it is overloaded. For this reason, many circuit breakers are now designed to use electromagnets, which we will discuss in the next topic. When wiring, both the wire and the circuit breaker are carefully selected to meet the current demands of a circuit. If the current is to carry currents as large as 30 amps, a heavy-duty wire and an appropriate circuit breaker must be used. Household circuits that are normally used to power lamps and small appliances often require only 20 amps. Each circuit has its own circuit breaker to accommodate its maximum safe load. As an example, let's consider a circuit that powers a toaster, a microwave oven, and a heater, represented by R1, R2, and R3 in the figure. Using the equation P equals I delta V, there it is, we can calculate the current carried by each appliance. The toaster rated at 1,000 watts draws a current of 8.33 amps. The microwave oven, um, rated at 800 watts, draws a current of 6.67 amps. And the heater, uh, rated at 1,300 watts, draws a current of 10.8 amps. If the three appliances were operated simultaneously, they draw a total current of 25.8 amps. That means that the breaker should be able to handle at least this much current or else it will be tripped. As an alternative, the toaster and microwave oven could operate on one 20 amp circuit with the heater on a separate 20 amp circuit. Okay, many heavy duty appliances, for example, electric ranges and clothes dryers, require 240 volts to operate. The power company supplies this voltage by providing, in addition to the live wire that is 120 volts above ground potential, another wire also considered live that is 120 volts below ground potential. That means the potential drop across the two live wires is 240 volts. An appliance operating from a 240 volt line requires half the current of one operating from a 120 volt line. Consequently, smaller wires can be used in the higher voltage circuit without becoming overheated. And I think I'll continue on with electrical safety. No, let's put it on its own. Uh, we'll put it on its own recording.